The goal of the study is to design and analyze 3 controllers on a virtual inverted pendulum on a car system with realistic actuator dynamics and constraints. To understand the performance of all types of controllers, we chose 3 different controllers. 2 classical controllers, LQR, PD, for linear time invariant systems, and 1 modern controller, MPC, for nonlinear time variant systems. The car pole system was moved by a motor belt pulley system shown in Figure 2. The inertia of the pole and frictional force was neglected. The nonlinear model was obtained through Euler-Langrangian formulation that includes the actuator dynamics and constraints. A state space linear model was obtained by linearizing the nonlinear model about the equilibrium point using Taylor expansion. The actuation input had absolute limit of 36 volts with soft limit of 12 volts, lasting maximum of 1.5 seconds, since a short burst of overvoltage is allowed in real systems. We used an existing commercial brushed DC motor for the study. MATLAB and Simulink were used for simulation for 3 trials. Each trial used one of the controllers starting from 0 initial condition to reach a desired position of 0.5 meters and stable equilibrium position within a simulation time of 25 seconds. For each trial, tracking performance, energy usage, and computational time were analyzed. The control objectives are shown in Table 1. LQR is a full-state feedback controller that optimally finds the gains given the weight on the tracking performance, matrix Q, and control effort, matrix R, by solving the given cost function and system dynamics. For PD controller, we used 2 PD controllers where the input to the plant was a sum of the 2 controllers. MPC is a relatively modern feedback controller for nonlinear systems that optimally finds the actuator input by running multiple predictions of the plant model for various actuator input values for a short period of time in the future, also known as prediction horizon. The controller is strategically computed using the actuator input values for a brief period of time, known as control horizon, using an optimizer by minimizing the cost functions while satisfying the input and output constraints. These are the simulation results for each trial. All controllers met the control objectives and only little steady-state errors were observed. The MPC exhibited the lowest settling rise time as well as steady-state error. The control input was higher in magnitude and fluctuating more compared to other controllers. The LQR and PD exhibited similar tracking performance. Both had larger settling time, rise time, steady-state error, as well as smoother state tracking and control effort compared to MPC. In particular, the PD controller had a smoother tracking and control effort than LQR and MPC. Each controller had distinctive pros and cons. MPC had the best tracking performance and highest energy efficiency with the expense of the longest computational time. This was expected since MPC required computation of numerous predictions of the plant model and optimizations of the actuation input for every loop. Also, MPC had too many control parameters that depended on one another, making it difficult to tune. The LQR and PD both had smooth tracking performances with shortest computational time. The short computational time was expected since the equations were all linear and did not require predictions of the plant model. The LQR had the most intuitive design and tuning process since it required only 2 most relevant control parameters such as Q and R matrix without worrying about the coupling effect between the input and the outputs. However, the PD took a long tuning time due to coupling effects of the input and the outputs. Also, both LQR and PD had slow tracking performances and higher cost of transportations compared to MPC. It is interesting to note that the PD had smoother state tracking and control effort than LQR. This resulted in lower power consumption and thus cost of transportation. To conclude, the ideal controller really depends on the engineer's requirement. While LQR or PD is more practical for controlling physical systems online with limited computing resources, MPC can be more practical for controlling virtual systems offline and if the tracking performances were critical. Thank you. The next few slides explain the system, controller, and evaluation parameters in detail.